Now let's do one example which we use virtual work to calculate the deflection of a frame. So this is problem worksheet number 9, problem 1, question D. And it's very similar to the example that we saw in the lecture. So I have a frame like this, a hinge, and another frame on the other side. There is a pin here. There is a pin here as well. If there wasn't any hinge over here, this would have been indeterminate. But because the hinge is over there, it helps me calculating the unknowns or my reactions. Yeah, so this is an internal hinge, which, remember, moment at it is 0, so it doesn't allow any transfer of moment. But because it's in the middle of the beam, if the whole beam goes to the left, the hinge will go to the left as well. If the whole beam goes up, the whole hinge will go up as well. So it doesn't act like a pin which is fixed to the ground. Yeah, so my pins over here, if I call these A, B, C, D, and E, these guys will have a reaction, a vertical reaction and a horizontal reaction. This guy will have a vertical reaction as well as a horizontal reaction. But my hinge, which is in the middle, won't have any of these reactions. The only point is it allows moment to become 0 and 0 here because it allows moment, like the door hinge. In this case, we have an applied load as well, an applied load of W. This is a known load. This is the applied load. This is the human being standing on the hinge. And the lengths over here to here and over here to here, let's say these are 4A and these are 4A, and the entire height of the column is 3A. Vertical deflection at C. So under such load, what will be the vertical deflection? What we do, we solve once for the real frame on the real load. Later on, using the virtual work, we replace this W with a unit load and we apply it to the point that the deflection is needed. Our lock is asking us for C, so it will be replacing W. If it was asking for D, you were applying it at point D. So let's begin. Let's zoom in again. Okay, that's my frame. Let's figure out what is VA, what is VE, HE, and HA, because whatever we find over here, then these will be transferred here, and then the same thing will transfer here. If you remember, for the frames, we weren't writing functions. We were actually jumping all the way to the diagrams, because these were the values. On the other side, looking at this frame, you can clearly see that it's very symmetric. So if I just calculate whatever is happening on the left side or on the right side, the other side is the same thing as well. So it's symmetric. In the previous example in the lecture, one side was A, the other side was 2A. But over here, I'm perfectly symmetric. So let's start. Summation of all forces in X direction equals to 0. Getting this direction as positive. This concludes that HA is equal to HE. Okay, so far so good. Summation of all forces in Y direction equals to 0, going upward. So I have this guy, and this guy. So I can say summation of these two equals to this. V of A plus V of E is equal to W. Perfect. And let's go for a moment. Equals to 0. This direction positive. So far very similar to what we have done in the lecture notes as well. Let's take a moment along point A. Anyhow, really doesn't matter, A or B. If I take the moment along point A, these will be gone. I have this one with a perpendicular distance of 4A. I have this guy with a perpendicular distance of 8A. And That's it. So W going around A is clockwise, so it will be positive. W times its distance 4A. W perpendicular distance 4A. This guy going around A, V of E going around A is against my direction, so negative. So negative VE times its distance is 8A equals to 0. I can figure out what is VE from here. So VE is equal to 8A divided by 4A will become W over 2, half a W. If this is half a W, then V of A is half a W as well from this. So let's say number 1, let's say number 2. Still haven't figured out these guys. The good thing is I have a hinge, so I can cut one side and write one single more moment equation as well, because this hinge in the middle omits the moments going around, so I can consider this side as a separate side from the other side. So let's see. Let's draw it first. So I'm considering the right side. This is my hinge. This is my bits, and I'm cutting it from this side. Yeah, I have the pin. This is 3A. This is 4A. Anything else? Yeah, so I'm cutting a bit before the hinge. Yes, so actually if I draw it correctly, it's here, so I am getting rid of this. So I have 1 VE, which I have already calculated is W divided by 2, and I have 1 HE coming in, which I'm interested in finding it as what is the value, and then this is 4A. So let's say summation of moments along point, if this is E, D, and C, similar to the class. If I get it through point E, I will get rid of my unknown. I want my unknown, so I take a moment along point C now. Equals to 0. Positive will be HE times its perpendicular distance to point C, and it is going positive along point C, you see. So it will be HE times 3A, and then I have this W divided by 2. What is the perpendicular distance? 4A, and going around point C it is negative, so negative W divided by 2 times 4A equals to 0. Now this will be 2AW divided by 3A, which will be 2W divided by 3. HE will be 2W divided by 3. Let's call this number 3. If this is this much, if I put it here, HA is the same as well. So HA is then equal to 2W divided by 3. Oopsie. Let's call this equation number 4. So far so good. I have calculated this, I have calculated this. I know these bits are fixed, so whatever moment is in my column will be transferred to the other side as well. And let's carry on. So I just zoom out. I'll bring a paper. Now, instead of like following what the lecture was saying, that I will cut it here and I will cut it later on here. Let's do it a little bit with our mind. So looking at the values that I have this value and I have this value. I can say that the moment over here is 0 and the moment over here is 0. Can I say that the moment over here is actually this guy times its distance? So HA times 3A. Yes. The same thing happens here as well. Whatever HE is, which they're equal, times 3A. And whatever the moment here is, the moment on the other side will be the same as well. Now it's the matter of where to draw the moment diagram. And we said, okay, we consider how the shape is deforming and we will draw it for the tension side. So this time, my frame is actually exactly like what we had before. Symmetric, a point load is applied. So this comes downward. As you can see, where are the tensions? Tension, 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 tension. So I'll have to draw the moment diagram for outside of the column, the moment diagram for outside of the beam, outside of the beam, and outside of this column. Let's draw it. So I'll draw a frame. I do my pin. The only thing which will cause a moment over there is HA, which I have already calculated. HA is 2W divided by 3. The same thing happens here as well. They're symmetric, so HE is 2W divided by 3. I have 1W applied here as well as a load. So if the length of this guy, let's draw it with another color. If this is 4A and this is 3A, if I'm drawing the moment diagram, I know moment at hinge is equal to 0. I know moment at pin support is equal to 0. So I expect my moments to come to 0, to come to 0, to come to 0, to come to 0. The only problem is here. And the only thing which is causing a moment here is this guy. If this times its perpendicular distance is 3A times 2W divided by 3, I can simply draw this. And why am I drawing it outside? Because we just saw the deflection. It was outside as tension. So it will be 2W divided by 3 times its distance 3A. So this will be my moment diagram. And as the example indicated, whatever happens here, the same thing happens here as well. Why am I drawing it outside of the beam? Because again, as we saw it in the deflection of the shape, the tension was outside. How much is this? Is this much. Exactly whatever is here, here is the same as well. So if this 3 with this 3 goes, it will be 2WA. And then over here will become 0. So now we said it's symmetric. So these were pin and these were pin and this was the hinge. And it's a symmetric. So what happens? Whatever happened on this side will happen on the other side as well. So this will go up and this will be 2WA. The same thing happens here as well, equal to that 2WA, which we know how 2WA came out is 2W3 times 3A. This 3 with this 3 will go, 2WA will be left. And this is the moment diagram. Voila, well done. This moment diagram is the real case. We want the vertical deflection at C. So beside the real case, I should have a virtual case as well. One easy way is to just replace this W with 1, and if W is replaced by 1, this will be 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 replaced by 1, because the reactions have been replaced by 1. I suggest that you do it once, step by step, exactly all of these, by replacing W with 1. But trust me, you should end up with such results. I draw the same curve again, pin and pin. Now this time I'm replacing it with one single unit load. This is my virtual case now. So if I replace W with 1, this HA for the virtual case will be 2 over 3. This HE for the virtual case will be 2 over 3. See, W, I replace it with 1 because it's the virtual one. I apply a single unit force at the point of interest. The question is telling me I'm interested in deflection at C. If this was C, so if this was A, B, C, D, and E, I'm applying a force 1. Luckily, the actual force was applied at that same point as well. If it was applied from here or here, then I couldn't have done this like this fast. I should have calculated again. But anyhow, now I'm lucky. So this will be 2WA will be 2A. Just replaced W with 1. This one will be 2A as well. At hinge, the moment is 0, so it went all the way to 0. Over here will be the same as well. 2W, 2WA. So W will be replaced by 1, so it will be 2A. And over here as well, the same thing. 2A. This is a rigid joint, this is a fixed joint, so the moment is transferred completely to the other side as well. Over here and over here. The actual one as well, you see, fixed joint. Or as we call it sometimes, rigid joints. All the moment is transferred through here and through here. If it was a pin joint, then we had something else. The pin joint wouldn't have transferred the moment. Now, all of these correct. I still want the deflection. All of these nice, but so what? I need the deflection. So let's write down the formulation. It was 1 times delta, which is my deflection, integration of moment function from the virtual, actual moment function of the frame, E representing the material, I representing the second moment of area, which represents the cross section, D of X. We said for the frame, you have to do this 0 to L for every single segment. So in reality, is this from A to B plus B to C plus C to D plus D to E. So the moment, the virtual moment times the actual moment of A to B, the virtual moment and the actual moment of B to C, the virtual moment times the actual moment of C to D, and the virtual moment and actual moment of D to E. We have kind of calculated this. We know the values, and these are the actual functions. So let's put them in. So the integration for the entire system, the entire frame, whole system, can be divided into A to B, B to C, C to D, D to E. Yeah? And that makes our lives easier. So I go A to B, which means the virtual moment times the actual moment, the real case moment, over the length of it. The length will be from, for example, from here will be 0 all the way to 3a. This will be my L. And remember, 2a times this is equal to 2wa. Over here, a is actually the one which is changing, yes? Because it's changing with length, as it's 3a. So a times a to the power of 2, if it goes under the integration, will be a to the power of 3 divided by 3. I bring out that divided by 3, so it will be 1 over 3 e, let's write it like this, 1 over 3 ei times, I'm bringing out from the integration, 2a times 2wa times 3a. What's happening? This is mx, this is the capital mx, so this and this 2wa, and this is actually the length of what this was, a to b. Now plus another one of these, this time another 2a, another 2wa times its length. Now I'm b to c. What is the length? Is 4a times 4a. I'm just doing the integration in my mind. If you're having trouble with this, do it step by step and it will be fine. M of x, and this is the L. What is this? This is b to c. So this done, this done. Now let's do d to c. So plus 1 over 3 ei times 2a times 2wa times its length of b to c, which is 4a as well. Yeah, so this to this was symmetric, so it was 4a times 4a. So again, the virtual moment, the actual moment, the length, and this was d to c. And then I have e to d, so it will be the last part, plus 1 over 3 ei times 2a times 2wa times the length of this guy, which is 3a. So this bit is for e to d or d to e, doesn't matter. This virtual, this the actual, and this is the length. Now if I sum these up and simplify them, what will happen? I can say, let's take all of these out, and let's take all of these 2a's and 2wa's out as well. So we'll leave with 3, 4, 4, 3. So will be equal to 1 over 3 ei, all of these are under this, yeah, times 2a, 2wa, I'm just getting a factor out of all of these, times 1a times 3, 4, 4, 3, 3 plus 4 plus 3 plus 4. So this and this and this and this equals to, all of these will be 4 and 4, 8 plus 6, 14 times 2 divided by 3. It will be 18.67 w a to the power of 3 divided by e I. This is the deflection value when point load W is applied at point C. C will come this much downward. So if I know what is the length of A and I know what is the force W, I know the material E, and I know the second moment of area of those cross sections, I can calculate the deflection. You see, I wrote the integration for the entire system, but then I divided it into the first column, the beam, the other beam, and the second column. Now imagine if we had the same situation. So I had the same similar frame with 1W applied here, but I was interested in knowing what is the deflection, if this is A, B, C, D, E. I was interested in deflection at point B, but in horizontal direction. Then the first bit would have been the same, perfect. This would have been the same, but the second bit, instead of applying a load here, I should have applied a virtual load here at point B, which the question is asking, and horizontal direction. Then I would have got rid of this, I would have had the moment diagrams, and then I would have continued exactly the same way. So try to solve this as well and see what happens. So that is tutorial number 5. This concludes our lectures, and this also concludes our tutorials. Hope you learned something throughout this 10 weeks, 9 lectures, as well as 5 tutorials, as well as some live sessions that we had. The whole intention was to teach you how to calculate bending moment, shear forces, axial forces for different types of structures, from trusses to beams to frames. We had a schedule, and until this moment we have followed the schedule. So hope you enjoyed it, hope you learned something new. Continue learning and practicing this course a lot, because next year and the years coming after that, you will be using the basics that you learned in this course in every single structural course that you have. Thank you very much, keep safe, and we'll see you later.